Good morning, students. Today we will continue with gas chromatography. We have finished with the theory, we have finished with the instrumentation, and I just wanted to tell you something about the efficiency of separation. So that's what we will be dealing with today. Before that, we will see about certain terms that are used while analyzing gas chromatograms. These terms we will see first, and then we'll go for the evaluation of the separation by gas chromatography. So the first term is peak base. What is peak base? An interpolation of the baseline between the extremities of the peak. I will show you with a diagram. Just go through these explanations of each term. I will show you with a diagram, with a chromatogram. Peak area is the area enclosed by the peak and the peak base. So you have, say, a peak like this, the area enclosed by the peak and the base of the peak, the triangular portion that is. Peak height, the distance from the peak maximum to the peak base. That's very clear. Peak width, the magnitude of the peak base intercepted by the tangents to the inflection points of the peak. This again, I will tell you with the diagram. Retention time TR, the time between sample injection and the appearance of a solute peak at the detector. Then you have dead time, which is T0, or it can also be T small m. Okay, the time for mobile phase to pass through a column. This is the time for only the mobile phase to pass through the column, assuming, of course, that mobile phase is not retained by the stationary phase. Adjusted retention time, T dash R. This is the time solute spent in the stationary phase. You will see what is the difference once I show you the diagram. It is the time that solute spent in the stationary phase equals T dash R, which is TR minus T0 or TR minus TM. So TR is the retention time. It is the time from sample injection to getting retained on stationary phase takes some time. So that's extra time TR. And here it is from only the time that the sample spends in the stationary phase. So we have seen adjusted retention time T dash R equals TR minus TO or TR minus T0. The capacity factor K dash is used to describe the migration rates of solutes on columns. Capacity factor is another thing that is very important. It helps you to know how much of stationary phase has to be loaded, how much of sample can be introduced. For solute A, say capacity factor for solute A, K dash A equals TRA, this R should be a subscript, TRA, that means TR, retention time for solute A, minus T0, that is the dead time, divided by T0. You can also write it as TRA minus TM by TM. That will equal to T dash RA by T0, because this T dash R is TR minus TO. Another term used is selectivity factor, alpha. How good your separation will be can be made out from the selective factor. Selective factor of a column for the two solutes A and B in a mixture is defined as alpha equals K dash B by K dash A. Okay, so we go further. Now we will see, we'll just try to recollect some things about the chromatography as it takes place, and then we will come to the evaluation part and see how efficiency of separation is determined. A chromatogram is a graph showing the detector response as a function of elution time. So you have on the x-axis, you will have time, and on the y-axis, you will have detector response. So depending upon the detector, whatever is being measured, that will be taken on the y-axis. X-axis will be time. Then the retention, then you get what is called the retention time. So what is retention time, TR? For each component is the time needed after injection of the mixture until that component reaches the detector. So it is the time when it is introduced or injected into the system and till the time it reaches the detector and is detected. So here you have a chromatogram. This is a standard, this is no name, which is another standard, and this is your unknown. So for your unknown, to find out the retention time, you will take, you'll measure from here to here. This is TR, from the point of injection till the peak, where you get the apex of the peak. So this is TR. What is adjusted retention time, T dash R? It is this TR minus Tm. So this is Tr minus Tm. That will be adjusted retention time T dash R. I hope it is clear now. You can also have retention volume. So retention volume VR is the volume of mobile phase required to elute a particular solute from the column. See, in gas chromatograms, you can either have on the x-axis the time or you can have volume. If you have volume, then you will be getting retention volumes different for different substances that are getting eluted. If you are using time, you will get retention times for the different substances. This retention volume or retention time is used to identify a particular peak as to what component is giving rise to that peak. So retention volume VR is the volume of mobile phase required to elute a particular solute from the column. It can be calculated as VR equals TR into F. What is F? F is the mobile phase flow rate. So in other words, suppose you are using volume on your x-axis and you're measuring retention volume, but you want to know the retention time, then you will divide this retention volume by the mobile phase flow rate. If you do that, you will get the retention time. The dead time Tm is the time of travel of unretained mobile phase through the column. This I've already told you, and sometimes Tm, and some people use T0 also. The adjusted retention time T-R for a solute is the additional time required for solute to travel the length of the column beyond the time required by unretained solute. So it is a subtraction of Tr minus Tm. Other than the time required by an unretained solute, what is the extra time required by the solute? That is T-R. In GC, Tm is usually taken as the time needed for methane to travel through the column. That's why you saw the methane peak in that chromatogram. For any two components, 1 and 2, say you have two components, 1 and 2, the relative retention alpha. Relative retention alpha, this is also the selectivity, is the ratio of their adjusted retention times. So for two substances, 1 and 2, alpha will be equal to ratio of P dash R to adjusted retention time for second component divided by T dash R1, adjusted retention time for first component. So first component is eluting first and second component is eluting second, where T dash R2 is greater than TR1. If the first component is eluting first, it's eluting later, and the second component is eluting first, then you will have to reverse this. Basically, it is selectivity equals the ratio of adjusted retention time of the more slowly eluted component divided by the faster eluted components retention time. This is done so that alpha should be greater than 1. What is capacity factor? We finished with selectivity, now capacity factor. For each peak in the chromatogram, the capacity factor K dash is defined as K dash equals TR minus TM by TM. Okay, this is adjusted retention time by the time taken for an unretained substance to move, or the mobile phase. So K dash equals time solute spends in stationary phase divided by time solute spends in mobile phase. Okay, so this solute spends in mobile phase or mobile phase to traverse the column. It's the same. So that could also be said as moles of solute in stationary phase by moles of solute in mobile phase. So K dash can also be said to be equal to moles of solute in stationary phase by moles of solute in mobile phase. So for moles, what we can do is concentration into the volume for solute divided by concentration for the solute in stationary phase and concentration into volume for the solute in mobile phase. But what is concentration of in stationary to concentration in mobile? Nothing but the distribution coefficient capital K. So here we can introduce capital K, that is distribution coefficient, into volume of stationary phase by volume of mobile phase. So that could also be written as TR minus TM by TM, which is equal to T dash R by TM. So these are different ways in which you can calculate depending upon the situation. So you can calculate capacity factor using this, or you can calculate capacity factor using this, or you can calculate capacity factor using this formula. So different ways you can calculate capacity factor. Capacity factor helps you to determine how much of sample can be introduced, because it also tells you about how the stationary phase is inside the column. The capacity factor should be maintained constant for a given set of stationary and mobile phase and sample, because if the capacity factor keeps changing, that means that there is some deterioration in the stationary phase or there is change in the mobile phase flow rate, provided the stationary phase and mobile phase substances are the same. Relative retention, or an alternative expression for alpha or selectivity. T dash R2 by T dash R1, K dash 2 by K dash 1. What is this K dash 2? K dash 2 is, or K2 by K1. Now all these, any one can be used depending on what information you have. Separation. The first thing which will give you some idea about the efficiency of your separation is resolution. So what does resolution mean in chromatography? So we will see about that. Solute moving through a column spreads into a Gaussian shape with standard deviation sigma. Common measures of breadth are, we will get, you all understand a Gaussian shape, okay, with a peak and equal distribution on both the sides. So standard deviation is given as sigma. What all we can measure? The width, W half, which is measured at half height. I will show you again a picture for this. The width W at the baseline between tangents drawn to the steepest parts of the peak, that is inflection points. So this is your Gaussian shape peak, is the detector response versus time or volume, and this is when the injection is done. Okay, so here you are getting TR. If it is volume, then you get VR. Okay, now this is the peak. And how do you get W half and how do you get W? This is the height of the peak. This is a straight line with the baseline. You extrapolate this. Now you see the distance here. This is height. So half the height would be this much. At this point, what is the width of the peak? This is W half. Okay, and here this is the steepest part of the curve. So through the steepest part, and also this is the point of inflection, you will draw a tangent. Again, you will draw a tangent through this part of the curve. This is the steepest part. You'll see these are not very steep. This part is the steepest part where the slope is greater. Okay, so here you will draw another tangent. You will see where the tangents intersect with this baseline, and from here to here is called the width of the peak. This is width of the peak. It will be 4 sigma. What is sigma? The standard deviation. This will be 2.35 sigma. I hope it is clear now. What is width of peak and what is W half? Now we'll see something about resolution. See, if resolution RS is 0.5, when do you get this? When you get a peak like this. Actually, there are two components, but the summation is seen like this with the width equal to 2 sigma. Okay, what has happened here is that this is one peak and this is one peak. Lot of overlapping has happened between the two peaks. So this is not an acceptable situation. Resolution of 0.5 is not acceptable. You go to resolution of 0.75. What do you see? Now you see that there is a small dip. This was looking like a single peak. Now you can easily make out there are two peaks. But the two peaks have not been separated. That also you can make out. So how do this peak continues like this continues like this, and there is an overlapping here also. This is also not acceptable because the overlapping is too much. Then you come to if resolution is 1. You see the distance between the peaks is going on increasing as the resolution is increasing. Resolution is 1, still you see an overlap. So in most cases, this is also not advisable. You see the distance between the peaks is 4 sigma, sigma being the standard deviation. Now, what you can see here is the peak is coming like this, and this part of the peak has not touched the baseline. And hence the resolution, if you calculate, it will be only 1. This is when the resolution is 1.5. This is the ideal situation. Here it touches the baseline. The first peak comes to the baseline, then the second peak, and the distance between the peaks should be at least 6 sigma. So this is an ideal condition where we have got a very good resolution. Sometimes 1.2 resolution is also acceptable because the mixing, the overlapping part will be very small, and it depends upon what type of analysis you are doing. So many cases that may be acceptable. But when you are developing a method, aim for 1.5 to 2 resolution. That gives you the best separation. So separation of mixtures depends on width of solute peaks. You want narrow peaks. The solute peak should be narrow to get a good efficiency, and the spacing between the peaks should be large to get good selectivity. So this is what your aim should be. So is it possible to have too much of resolution? Yes, it is possible, but that's not a good method. So here we are seeing an overlapping where the resolution is 0.8 approximately. This is poor resolution because there is lot of overlapping. Adequate selectivity is there because the separation is okay, but poor efficiency because it has not got separated. You can have this or you can have this. Now here what you see is there is a good resolution, lot of separation, selectivity is good, but when you have a lot of baseline here without the next peak starting, then it is clear that you are ending up with the second peak getting eluted after a long time. So what ultimately happens? The complete analysis gets over only after a longer period of time, an unnecessary long period of time. If this peak had eluted here itself, then the analysis would have completed in a shorter time. Longer the analysis time, it will result in poor efficiency because of band broadening. Excessive resolution, you have here also RS is 2.5. I said 1.5 is sufficient. Excessive resolution, excellent selectivity and efficiency, but analysis time is too long. So this is also not acceptable. The most ideal situation is something like this, where you get good efficiency, adequate selectivity, satisfactory analysis time. And that corresponds to RS having a value between 1.2 to 1.5. So this is the best RS value to get the most efficient separation. This is the relation between resolution, selectivity, and column efficiency. Diffusion, a band of solute broadens as it, this you have to keep in mind always. A band of solute broadens as it moves through a column. Ideally, an infinitely narrow band applied to the inlet of the column emerges with a Gaussian shape at the outlet. See, this is what happens when you inject. You are injecting as a plug of vapor, so immediate injection. As it moves down the column, you will see that the band is spreading. Moves still longer, then it spreads a little more. And you can see the peak is also becoming broader. That is why unnecessarily having a very long column is also not desirable. The longer it spends time in the column, the more broader the peak. Now, the theory of chromatography, I don't know whether you have actually completed this. It should probably, it has been done in the introduction chapter of chromatography, but I will still try to refresh your memory, and we will see what are the theories of chromatography. These help in determining the column efficiency. So you have basically two theories, plate theory and rate theory. Plate theory is the older theory and it was developed by Martin and Synge. Rate theory is the theory that is currently in use. So we'll go through each of these, starting with the plate theory. Here, view the column as divided into a number of adjacent imaginary segments called theoretical plates. What it means is you have a column and you view the column as if there are a number of shelves or number of stages. These are imaginary stages and they are called theoretical plates. Within each theoretical plate, complete equilibration of analytes between stationary and mobile phase occurs. Okay, in one theoretical plate, suppose you have a number of shelves, then within one shelf, complete equilibration of analyte between stationary and mobile phase will occur. The distribution equilibrium will be established. So a little about theoretical plates. They represent a hypothetical division of chromatographic columns. It's hypothetical, it's not actual. Okay, that's why I said it's imaginary. And each plate represents an equilibrated partitioning of the solute between the stationary and mobile phases. So one equilibrium is achieved for the solute between the stationary and mobile phase. That much length of the column represents a plate. Having more theoretical plates increases the efficiency of separation process. More the number of theoretical plates in a given column, better will be the efficiency of separation. Why? Because more number of equilibria will be established. More the equilibria established, better is the separation. One obvious way to increase the number of plates is to increase the length of column. Doubling the length doubles the number of theoretical plates, but you have to do this with caution because you have to consider the square root dependency on the number of plates in the equation. You will just be seeing the equation. Before that, I hope you have also been introduced to countercurrent system, because chromatography basically developed from countercurrent system. What is countercurrent system and how it differs from chromatography? In countercurrent system, you have different apparatus or reservoirs. Here you have, in each of these, you will have stationary phase. The shaded part is the stationary phase. You will put in mobile phase, you will put your sample mixture. You will shake this, allow it to equilibrate, and then the upper layer, which will be the mobile phase, is transferred to the next receiver, which has already got same amount of stationary phase. This stationary phase is already there. It's a fresh stationary phase. This mobile phase, which has some amount of sample, will be transferred here. This is empty now. So fresh mobile phase is introduced. So when you are equilibrating, when you shake and allow it to come to equilibrium, there is a distribution of sample between stationary and mobile phase. Suppose both are liquids, then there is partitioning. The upper layer of mobile phase is transferred to the second receiver, which already has fresh stationary phase. And here you are introducing new amount of mobile phase, no sample. Again, both of these are shaken. Then they are allowed to come to equilibrium. They are allowed to settle. Then the mobile phase from this is transferred to the third one, okay, which already has stationary phase. The mobile phase from first is transferred to second. Fresh mobile phase is added. Like this, you will go through the number of receivers. Here, however, this is the same thing which was adopted in chromatography, but the only difference is here it is a stop flow. Here it is a continuous flow of mobile phase. The mobile phase here is not continuously flowing. It is equilibrating, then you transfer, again you equilibrate, then you transfer. It's like that, stop flow. Whereas in chromatography, it is a continuous flow. So what is the significance of plate theory? Greater separation occurs with greater number of theoretical plates, and secondly, plate height becomes as the plate height becomes smaller. As the plate height becomes smaller, you will get more number of theoretical plates. Say, for example, in a 10 centimeter column, each plate is 1 centimeter. Then you will have 10 theoretical plates. If each plate height becomes 0.5 centimeter, then you will have 20 plates. I hope you have understood. So the plate height, as it becomes smaller, you will get more number of theoretical plates in a given column length. And more number of theoretical plates will give you better separation. This is the equation. Length, L is the length of the L equals N into H, where L is the length of the column, N is the number of theoretical plates, and H is the plate height. H or HETP. HETP stands for height equivalent to a theoretical plate. This expansion is many times asked in question papers. What is HETP and what is its significance? So what is the significance of HETP? You can get from here. See, HETP equals L by N. So if the length is kept constant, number of theoretical plates should increase in order to decrease height. So you have to ensure that the height or HETP becomes small. This will increase the number of theoretical plates, and that will increase the separation efficiency. So important prediction of plate theory, there are two predictions. Band spreading. The width of the band increases as the retention time increases. I told you the longer it takes to elute out, the more broader the band. Faster it elutes out, the narrower the band. I showed you the picture also earlier. Secondly, the smaller the HETP, the narrower the eluted peak. And definitely that's why the more efficient will be the separation. Plate theory practical considerations. Not unusual for a chromatography column to have millions of theoretical plates. This is what is desirable. You should have millions of theoretical plates for a given chromatography column. Then you can definitely ensure a very good efficiency. Columns often behave as if they have different number of plates for different solutes present in same mixture. For the same mixture which has a number of solutes, for each of the solutes, the number of theoretical plates could be different because their distribution equilibria are different. They take longer or shorter time to achieve equilibria. So that will decide how many theoretical plates are there in a given column. So it's different for different solutes in the same mixture through the same column. Number of plates on column is given by this equation. You have n equals 16 Vr by Wb whole square. Instead of Vr, you can also have Tr, that is retention time or retention volume. Any one of that can be used, and this is the width of the peak at baseline. So base width of the peak. This equation is a measure of the efficiency of column because it shows whether you have more number of theoretical plates or less. High number of theoretical plates indicates efficiency of column. Low number of theoretical plates indicates efficiency of separation. Total retention volume VR, or adjusted retention time instead of retention time. So the effective number of theoretical plates, the only change is we are using B dash R instead of VR and or T dash R instead of TR. Now the next theory, that's rate theory. This is based on a random walk mechanism for the migration of solutes through a column. Random walk mechanism means it can go, you can walk from one point to another straight, or you can go to the right, come to the left, or left to right, or go in a zigzag fashion. That's random walk mechanism. From one point to the another, you can move in different ways. So what it takes into account, this rate theory, is the mechanism of band broadening, the effect of rate of elution on band shape, availability of different paths for different solute molecules to follow, and diffusion of solute along the length of travel. So this gives rise to Van Deemter equation for plate height. Plate height H or HETP equals A plus B by mu x plus C mu x. Very simple equation, but you should know this. So what is this? HETP, height equivalent to a theoretical plate or height of a plate. A is related to the multiple paths of travel available. B by mu x relates to longitudinal diffusion, and C mu x relates to the equilibration time. We will see each one of these and how we can ultimately improve the efficiency of our separation. In packed columns, all three terms A, B, and C contribute to band broadening. In open tubular columns, A is 0. So one of the terms is 0, and that's why the efficiency is always much better in open tubular columns. We'll see why A is 0. In capillary electrophoresis, this for your information, both A and C go to 0, so the efficiency will be still better. This is the Van Deemter plot. You will see that this is here the dashed line, this indicates A. A is actually the eddy diffusion. So this is A. How does it vary with the flow rate? It does not, it is not dependent on flow rate. Even if you increase flow rate, A remains the same. This is because A is dependent upon the packing and the variable flow paths through the packing for the mobile phase. We'll see in a little more detail. This, what you see here, a decrease, this represents B by mu x, the longitudinal diffusion. So here what you see, the faster the flow rate, as you increase the flow rate, longitudinal diffusion decreases. You want it to decrease. So to control this term, longitudinal diffusion, you need to have a faster flow rate. The third one, C mu x, which relates to equilibration time. As the flow rate increases, you see the C mu x also increasing. So to control this, we need to reduce flow rate. Why do you need to control each of these? You need to control A, you need to reduce B by mu x, you need to reduce C mu x, so that the sum which gives you the height of one theoretical plate also reduces. If you reduce all three, then your HETP will reduce. And if HETP reduces, automatically the number of theoretical plates will increase, and so will the efficiency of your separation. This orange colored graph, what you are seeing, this is the summation of all effects of all these three. So this is the Van Deemter plot actually. So here you are, this is A plus B by mu x plus C mu x, the overall effect. So what is minimum HETP? Equals A plus square root of BC. And what is optimum flow rate? Optimum flow rate equals square root of B by C. This is the way we can calculate the optimum flow rate, and this is the way we can also get the minimum HETP, giving rise to the maximum number of theoretical plates. So each of these terms now we will see and how to control them. Longitudinal diffusion gives rise to B by mu x term in Van Deemter equation. So solute continuously diffuses away from the concentrated center of its zone. Whenever you have a zone, on either side of the zone, there is less concentration, so there is diffusion towards the lower concentration. That's how zone broadening takes place. The greater the flow rate, the less time is spent in the column and the less longitudinal diffusion. The greater the flow rate, the time available for diffusion to occur reduces, and therefore diffusion also reduces. That's why we say B by mu x term reduces with greater flow rate. You can also see here B by mu x. The moment you increase mu x denominator, the ratio will start to decrease. So here you have zone of solute after short time on column. The longer it stays in a column, zone of solute after longer time on column. What happens? This was only so much wide, the width has increased. This is because of diffusion or spreading. From here it will spread here, from here it will spread here, because there is no solute here. So higher concentration to lower, higher to lower, again from there to there. So the longer it spends in the column, greater will be the diffusion, longitudinal diffusion. Because longitudinal diffusion in a gas is much faster than in a liquid, the optimum flow rate in gas chromatography is higher than in liquid chromatography. And we come to the last non-equilibrium or resistance to mass transfer term. This term comes from the finite time required for the solute to equilibrate between mobile and stationary phases. Some solute is stuck in the stationary phase, but the remainder in the mobile phase moves forward, resulting in spreading of zone. The slower the flow rate, the more complete equilibration is, and the less band broadening occurs. Because the slower the flow rate, full complete equilibrium is established, and you will have less band broadening. Otherwise, major portion remains in mobile phase and it keeps moving forward and spreading. You can see from this picture here, the top is mobile phase, bottom is stationary phase. This is the direction of movement. This is the bandwidth. If it is a slow equilibration, if it is taking a long time to equilibrate, then what will happen is the mobile phase by that time would have moved forward. And ultimately, the band that you see will be from this end to this end. So the bandwidth after some travel will be much greater than it was before. That's how the band starts increasing in its width if the equilibration is taking longer but the flow rate is faster. Plate height due to finite equilibration time, that is h, with respect to mass transfer, that is HETP, or height of a plate with respect to mass transfer is CUX. So this is the flow rate of the mobile phase. What is C? It is the total concentration in stationary and mobile phase. Concentration in stationary, concentration in mobile phase. So rate of CS describes the rate of mass transfer to stationary phase. CM describes rate of mass transfer to mobile phase. Specific equations for CS and CM depend on the type of chromatography. What type of chromatography is involved? Adsorption, partition, ion exchange, what type? That will ultimately decide, and whether it is liquid chromatography, gas chromatography, that also will decide CS and CM. So resistance to mass transfer, in this case, with regard to this variable, efficiency is increased by decreasing stationary phase thickness so that equilibrium will be established faster, reducing column radius. This will also establish it faster because lesser stationary phase will be there, and increasing temperature. This will also help in faster dissolution in this is in general, but in gas chromatography actually you will have to decrease the temperature because you will have to ensure a gaseous sample dissolving in a liquid stationary phase. So that for that you will have to actually decrease temperature. And yeah, the first one I have not dealt with, A, that is multiple flow paths, or it refers to eddy diffusion. The term A accounts for the multitude of pathways that could be followed through the column by one molecule. A equals 2 lambda dp, where lambda is a dimensionless constant characteristic of packing. This is the packing component. And dp is the particle diameter. So greater the particle diameter, more would be the eddy diffusion. So to reduce eddy diffusion, one way is reduce the particle size. Another is reduce packing non-uniformity. So here is a picture. You see all irregular pathways. Now 1, 2, and 3. 3 molecules are there. They're starting off at the same point, and they are traversing. The first one takes a very circuitous type of route. It goes through all these, a long route, and comes out. The second one, a little zigzag way, and the third one, almost a straight one. So this comes out fastest because the route is shortest. This is a little longer route, so it takes a longer time. By the time it comes here, the mobile phase movement or the time has come till here, and this takes still longer, so here, and that's how you get a peak which is very broad. So peak broadening takes place because of these different pathways available. So you have to control this, means your best way to do is to have spherical particles which can fit in properly with regular pore sizes and uniform packing and smaller particle size. That to a great extent will keep eddy diffusion very low and it will keep it to a minimum. Of course, this I also told A component is zero in open tubular columns. That's because open tubular columns do not have any packing. The column is actually empty. Only on the walls you'll have the stationary phase. But in between there is nothing. And that's why eddy diffusion is zero and the efficiency of open tubular columns is very high. The A term can be minimized by eliminating column packing and as in open tubular columns, reducing the particle size of packing and packing the column more uniformly with spherical particles of similar size. This is the effect. Smaller the particle size, lower the eddy diffusion. This just shows you the effect. So factors affecting resolution, a more usable expression for resolution RS equals 1 by 4 into square root of n refers to efficiency, into alpha minus 1 by alpha, that's selectivity, into k dash by k dash plus 1, that's retention or capacity factor. So all the three are important. So RS or resolution can be calculated putting all these values. So it can be shown like this also, where alpha equals kb by ka. Very important for column design, large changes in n are needed to improve RS. You have to, because it's a square root term. So you have to increase n by a large amount to increase RS. Separation can be increased by increasing L because n equals L by H, so increase L. But better to improve K and alpha. I told you L cannot be increased indefinitely. It leads to other problems. So better to increase K and alpha. For this, change the choice of stationary and mobile phase for separation of analytes of interest. So required plate number. If K dash 2 and alpha are known, required number of plates can be calculated using this equation. So this is the required number of plates in order to get a resolution value of 1.5. So from the required number of plates, you can then calculate the length of the column required. Okay, see, you can calculate the length of the column. You know n, you calculate L. You also know H. So you can calculate. This is the overall equation directly. And then what is the minimum analysis time? The time T, retention time, can also be calculated. The major objective in any chromatography is the highest possible resolution, to get the highest possible resolution in the shortest possible time. Optimization techniques always aim at choosing conditions that lead to desired degree of resolution with minimum expenditure of time. Time should be short, but you should get complete separation. So minimizing plate height can be done by reducing particle size, reducing column diameter, changing column temperature, reducing thickness of liquid film, optimizing flow rate of mobile phase. These are the different ways you can do it. Resolution also improves with length of the column, but it proves to be expensive in terms of time of analysis because that also increases. So variation in selectivity factor can be brought about by changing of column temperature, changing stationary phase, using special chemical effects. Capacity factor is the other one. Increases in capacity factor enhances resolution, but at the same time, at the expense of elution time, it will increase the analysis time also. So you should not have very high capacity factor. Optimum values are from 1 to 5. Easiest way to improve RS is by optimizing K dash. In GC, K dash can be improved by temperature programming. In LC, K dash is improved by gradient elution. So these are advantages of open tubular columns. I've already told you higher resolution, shorter analysis time, increased sensitivity, and lower sample capacity. This, when compared with packed column, you have so many advantages because it increases the linear flow rate, or a longer column, or both is allowed in open tubular columns. Decreased plate height, which means higher resolution. These are some, I will give you this, so you can, I told you about the various terms here along with the equation, and what are each of these terms is explained here very clearly. So ultimately, what happens? Last class also I ended with this, the different types of peaks. This is the ideal chromatogram that you should get, a Gaussian shape. Sometimes you may get like this, and sometimes you may get like this. This is pulled, that is, this one is dragged forward. This is called fronting. This takes place because of overloading the system with sample. More amount of sample is injected, then you see fronting taking place. What you should do is reduce sample injection. That will in most cases reduce this. Otherwise, it indicates problems with the column, stationary phase. And here you see, this is the latter part has been pulled. This is called tailing. The latter part is pulled here. So this takes place means what it refers to is the elution is not taking place well. So the component is very strongly adhering or remaining in the stationary phase. So elution is not taking place as desired. So you may have to change the stationary phase or the mobile phase to ensure that it comes out faster. In case of gas, you will have to alter the stationary phase only. This is fronting, this is tailing. Okay, so in fronting, you will see, if you see from the apex, this half is smaller than A is bigger, B is smaller. In tailing, B is bigger, A is smaller. Tailing, some part of the stationary phase binds analyte molecules more strongly, so elution doesn't take place easily. Fronting, some molecules move ahead because injected too much of sample, which saturates the stationary phase. So peak asymmetry, AS equals B by A at 10% height. This is from the baseline, 10% of the height. At this point, you have to calculate A and B. So 0.9 to 1.2 asymmetry factor or peak asymmetry is acceptable in chromatography. You don't need to worry. But if it is less than 0.9 or greater than 1.2, it is not acceptable in chromatography results. You have to be careful regarding this. So that completes your gas chromatography chapter.